Let's suppose you're watching your favorite football game on a live stream, and someone is just about to score a goal when all of a sudden the video starts buffering. You'd probably be pretty upset at this. And this is an issue that we were facing at Meta, and it happened when our layer 4 load balancer misrouted packets. And these misroutings had the most impact for live stream connections, but it was also a general problem for long-lived TCP connections. I'm Aman. I've been working at Meta for the last 4 years on the layer 4 load balancing team, and I'm passionate about solving problems in networks and distributed systems. Today, I and my metamate Andrii will talk about 3 techniques that we devised and implemented to reduce the incidence of misroutings in our layer 4 load balancer. But first, let's talk about what happens when a user sends a typical request to Meta. A typical request passes through a series of 3 tiers, and within each tier, it passes through a series of switches, and then it passes through a layer 4 load balancer, and then it passes through a layer 7 load balancer. Now, the difference between a layer 4 and a layer 7 load balancer is that the former directs packets based on information in the transport header. So this could be, for example, information in the TCP or the UDP header. And a layer 7 load balancer load balances based on information in the application layer protocols. So this could, for example, include information in the HTTP headers. Now, what we'll be focusing on in this talk is the brown boxes that you see in this diagram, which is the layer 4 load balancers. So let's take a look at how a layer 4 load balancer works. If you look at a typical TCP or UDP packet, it has 2 portions. It has a header and it has a payload. The header has numerous fields, but for the purpose of this talk, there are 5 that are important. And these 5 are the source IP, the destination IP, the source port, the destination port, and the protocol. And together, we call these the 5-tuple of the packet. So when the load balancer receives such a packet, it calculates a consistent hash of the 5-tuple and sends the packet to one of the backends based on the output of the hash. Now, we don't calculate the 5-tuple hash of every incoming packet. We maintain an LRU cache, which has mappings from 5-tuples to backends. So let's take a look at how this cache works with an example. Let's suppose the load balancer receives a packet. It's going to calculate a consistent hash of the 5-tuple, send the packet to one of the backends, and place the mapping from the 5-tuple to the backend in its cache. Now let's suppose a second packet arrives, but this packet has a different 5-tuple than the previous one. Now the load balancer is going to do the same thing that it did before, which is that it's going to calculate the consistent hash of the header of the 5-tuple, and it's going to send the packet to one of the backends and then place an entry in the LRU cache. Now let's suppose a third packet comes in, but this time with a 5-tuple that this load balancer has seen before. Then instead of calculating the consistent hash of the 5-tuple, it just refers to the entry in the LRU cache and decides to route the packet based on that. So we can summarize this logic as an if-else statement. If the 5-tuple of an incoming packet is present in the LRU cache, then we route it based on that. Otherwise, we calculate a consistent hash of the 5-tuple, route the packet based on the output of that hash, and place an entry in the cache. So now let's zoom out a little and look at what happens when a packet arrives at a cluster. The first thing that happens is that the packet passes through a series of switches. In this diagram, I've just drawn one for the sake of simplicity. The switch calculates a 5-tuple hash and sends the packet to one of the layer 4 load balancers. And the layer 4 load balancer calculates a consistent hash of the 5-tuple and sends the packet to one of the backends. And once this is done, the load balancer places an entry in its LRU cache. And this animation assumes that this entry wasn't already present in the cache in the beginning. So in a couple of minutes, Andrii is going to talk about the history of the load balancer and two techniques that we used to reduce the incidence of misroutings by our load balancer. But before that, let's go through some failure scenarios in the system. Let's suppose that there's a connection in progress in this cluster. And while this connection is in progress, one of the layer 4 load balancers goes down. What could happen now is that the switch could send subsequent packets for that connection to a different layer 4 load balancer. But this is still okay because all of the load balancers use the same hash function and the hash ring hasn't changed. So when a different load balancer receives subsequent packets, it can send them to the same backend as before. Now, let's suppose that a backend goes down. And let's suppose that this backend isn't the one that's handling this connection. Then the switch will decide to send packets to the same layer 4 load balancer as before. And now, although the hash ring has changed, this layer 4 load balancer has the state for this connection in its LRU cache, so it can still route packets to the same backend as before. Now, let's come to the more interesting scenario in which both a backend and a layer 4 load balancer go down. Now, in this case, what could happen is that the switch could decide to send packets for this connection to a different load balancer. And since the hash ring has changed and this load balancer doesn't have the state for this connection, it could decide to send these packets to a different backend. And this manifests as a misrouting. Now, this is more likely to affect long-lived connections because a topology change is more likely to occur during the duration of a connection if it's longer. And this is one of the reasons why Livestream is one application that's pretty adversely affected by this. And this misrouting is the cause of you being angry when you can't watch your favorite football player score a goal. Now, I'll hand it over to Andrii, who will talk about the history of the load balancer and two techniques that we devised and implemented to reduce misroutings in it. Over to you, Andrii.
Thank you, Aman. Hello, everybody. I'm Andrii. I'm a software developer on the traffic team. For the last 5 years, I've been working on various load balancers here at Meta. So, as Aman described, our load balancer, while it's not perfect, it worked really well for us for many years. We started to use it back in 2013, and since then it served us quite a lot of traffic. The important part in the development happened in 2018 when we migrated our implementation from IPVS to XDP-based called Katran. The most important benefit relevant to this talk is that it allows us to have a very easy programmability of our load balancer. In 2020, our teammates were rolling out support for Quick protocol in our infrastructure, and we have our own Meta's implementation of Quick library. In being at user mode, Quick allows for very easy instrumentation and this collection of various statistics. One of such important statistics in our implementation of Quick is count of the misrouted packets to the wrong host when the Quick packet is routed to the incorrect Quick server. So as our teammates were rolling out Quick support in our infrastructure, we noticed some spikes in misrouted packets. And while they were not critical, we thought we can do much better and practically eliminate them. Luckily, if we look at the Quick header, it has destination connection ID and source connection ID embedded in every packet. In a short form packet, source connection ID is not present, but our load balancer handles only incoming traffic, and thus we care about destination connection ID only, which is always present in every Quick packet. So with us controlling both load balancers and Quick servers, we can have both of them cooperate and provide some hint to the load balancer. Let's take a look how quick client and quick server exchange the connection IDs. So quick client start the connection with the initial packet. It picks connection ID value for itself, and also picks a random connection ID for the destination for the server. On receival of such packet, the server generates its own connection ID and sends it back to the client. After receiving the server-provided connection ID, for all packets going forward, quick client is going to use that provided server ID. So the important point here that for most of the packets of the quick connection, client is going to send the value that was provided by the server. And connection ID is just an opaque binary value. And since we control both servers, quick servers, and load balancer, our quick servers insert a hint for our load balancer to know which server is handling those connections. So that's what we do. We just dedicate part of the connection ID to the server ID hint. Let's see how it works on the end-to-end with client, load balancer, and the servers. The important part here that both load balancers and backends share a mapping server ID values to the IP addresses of the backends of the quick servers. So the quick client initiates the connection with the initial packet. It picks a random value for destination connection ID. And in load balancer, we check that this is initial packet. We know the value is random, and thus we use consistent hashing to pick the backend. In this case, we pick the backend 3. For the subsequent packets, quick client received a new connection ID from the backend, and all the packets going forward have this new connection ID that has a hint. So in a load balancer, we check that it's not an initial packet, and then we do a lookup in our server ID map. And from there, we know clearly which backend is handling the connection. So when we allow this functionality in our network, we practically see reduction to 0 of all misrouted packets for quick connections in our data centers, and the amount that we could see was almost 0. So it worked really well for us with quick, and naturally, we wanted to have something similar for our TCP traffic. We looked at the TCP header, and unlike with quick, we are not that lucky here, and there is no obvious destination connection ID field. However, TCP header has an options field, which we can embed our own headers there, and we can have a connection ID like TCP option that will carry the server ID along with every packet, along with every packet, similar as we do with quick. There is another complication with TCP. Unlike quick, which is in user mode, TCP's headers are written in kernel and is not as easily accessible. Luckily, our teammate Martin implemented the BPF extension that allows us to read and write TCP options easily. Let's look how it works end to end. The client starts with a SYN packet, load balancer receives it, knows it's SYN packet, and uses consistent hashing to pick the backend. In this case, we picked backend number 1 with a server ID 41. The BPF program writes a header with a server ID, which will be carried along with a SYN ACK back to the client. On receiving a SYN ACK, the client parses the header, the TCP options header, retrieves the value 41, stores it along with a socket, and then going forward with every TCP packet outgoing, we are going to write that TCP option with the value 41. So such packet goes to load balancer parses the options and sees our server ID hint there, and now we know exactly which backend it should send to. As Aman described earlier, when we lose both load balancer and backends, the consistent hashing may result in some percentage of misroute. So in such case, A client continues sending packets with a server-ready hint, and the new load balancer is handling those packets, but it has exactly the same map. It parses the TCP options the same way and knows exactly that server D41 should be sent to the backend. There's a couple small overheads with the solution. We require extra 6 bytes with every packet for this TCP header option. There's also some CPU on both load balancer client and servers to read, write, and parse the TCP options. However, in our rollout, we haven't seen any noticeable increase in CPU usage when we roll out this functionality. Another important limitation of this solution is that it needs both client and servers to cooperate. We need to install BPF program on both sides, and that requires to have a control of both clients and servers for this to work. Additionally, we need to control over the network in between. Primarily, some firewalls may strip unknown TCP options. So the solution works really well for us at Meta because we control both within our data centers, where we control both clients and servers with the traffic from our edge CDN network to our data centers. It works really well in those cases. However, it doesn't work for the public internet access between clients and our edge CDN network. And Aman will describe a solution for that. Thank you all. Back to you, Aman.
Thank you, Andrii. As Andrii had explained, we embed routing information in quick connection IDs, and this helps us to reduce the incidence of misroutings for quick packets. And for TCP connections that are within our internal network, we insert a TCP option in the header, and this option contains routing information within it. And this helps us reduce misroutings for TCP connections within our internal network. However, if we look at TCP connections from a client to our network, we can't use TPR there. And the reason is that if we insert a custom option in the TCP header, then a middle box could sanitize this away or simply drop the packet. So we need an alternative solution that'll work from the client to our network. And we developed a solution called the shared flow cache for this subset of connections. And this works on the simple principle of state sharing. But before I describe how exactly it works, let's just do a quick recap of the LRU cache. When Layer 4 load balancer receives a packet, it calculates a consistent hash of the 5-tuple and routes the packet to one of the backends based on the result of the hash. And then it places the mapping from the 5-tuple to the backend in its cache. So this load balancer has the state for this connection. What we could do if we want to reduce misroutings is that we could broadcast this state across all of the load balancers in a cluster. However, if we do this for all connections, that would be excessive. So instead, we have to prioritize. So what we did was that we picked the connections that would give us the most benefit for the least cost. And for us, that would be live stream connections. Now, if you look at a premium live stream, then that could be viewed by tens of thousands of people. And if there's a misrouting there, then a user watching that live stream could see about 10 seconds of buffering. And this has a pretty big user impact. So this is the subset of connections that we decided to prioritize. So let's take a look at how this works. If you look at a cluster, it has layer 4 load balancers and it has backends. And what we did was that we introduced a central component that would receive 5 tuples from the backends for premium live stream connections. And this central component would broadcast these 5 tuples to the layer 4 load balancers. Now, if we assume that there's a premium live stream connection going on in a cluster, then even if layer 4 load balancer and a backend go down, then that's still okay because all of the layer 4 load balancers have the state for the premium livestream connection so they can all make the same decision. And this technique helped us reduce the incidence of misroutings for this subset of connections by about 90%. But one disadvantage of this, though, is that we can only prioritize a subset of connections that we want to improve, because otherwise, if we do this for every connection, that would be a massive amount of state sharing. So this selectively helps certain connections. So it's not like a quick connection ID routing or TPR where it benefits all connections. So that concludes our talk. I want to thank Udeep Pant for the work that he did in implementing quick connection ID routing and TPR. I want to thank Martin Lau for the kernel patches that he submitted that made TPR possible. I want to thank the Layer 4 load balancing team at Meta for all of the support that they provided us. And finally, I want to thank you for listening into this talk.